Fine. So these two spheres, masses 2 kg, 4 kg, velocity is 10 meter per second, and the other one at rest initially. Assume they undergo a collision whose coefficient of restitution is 0.5. Calculate their final speeds. Rishi, can you tell me the formula for coefficient of restitution? By definition, what is the formula for E?
Sir, it's 0.774, the value.
Where did you get 0.774 from? That was
Like,
only for that question.
oh,
See, E is coefficient of restitution. It depends
oh,
on
it's relative speed of separation by relative speed of approach.
correct, correct. So we write it as V2 minus V1. Not we write, we calculate it as V2 minus V1 by U1 minus U2 along the line of impact. Okay. Solve this. You begin by assuming they have final velocities V1 and V2. And you know, like when one sphere goes and collides with another, the force they exert on each other, that is a normal force, is an internal force to this system. So linear momentum conservation is applicable here. We'll assume both final velocities are to the right. If you assume that way, writing equations will be easy. Okay. Do it quickly. Write the linear momentum conservation equation and the equation for coefficient of restitution. Why will you subtract 10 and V2?
Because after collision,
Hmm.
there should be some speed lost, right? So when we're taking V2, we should have, like, the new speed will be lesser than 10.
See, whose speed was 10? Let's name these spheres A and B. Which one's speed was 10?
The silver A.
A speed is 10. B speed is initially 0. Now A goes and collides with B. Definitely A should lose some velocity. Finally, what symbol are we using for A's speed or A's velocity?
V1.
Then why are you saying V2 should be less than 10, more than 10?
Oh, yeah, Saman.
Okay, fine. Rishi, tell me how you'll write the linear momentum equation in this case.
The P initial will be
Hmm.
20 plus 4. No, not 0, because
Okay, should be equal to
uh 10 minus.
why 10 minus? You are making things complicated. We assumed their final velocities are V1 and V2. Use them directly in the equation.
2V1 plus
Hmm.
4V2.
That's all. That's the linear momentum conservation equation. Next is coefficient of restitution. You are told that coefficient of restitution is 0.5 is equal to directly substitute V2 minus V1 divided by U1 minus U2. U1 is 10, U2 is 0. That's all. So you get V2 minus V1 is equal to 10 into 0.5 is 5. This is the second equation and this is the first equation. You solve both of them, you can calculate V1, V2 separately. Is this clear? Any confusion in this? Rishi?
No, sir, understood.
Okay. Okay. That's all. You solve the equations. You will get V1 as 0 and V2 as 5 meters per second. So the first sphere A comes to rest and B carries the momentum after the collision. Okay, that is what the answer tells us. Okay. Now they can further ask you to calculate the change in kinetic energy or loss in kinetic energy, percentage loss in kinetic energy. Such things also can be asked. Fine. Let's try another problem. Assume this is the ground and let's say a ball is dropped onto it. Okay, let's consider this one itself. Assume it's dropped from a height h. Rishi, can you describe what is going to happen?
Then it'll fall and then it'll bounce to a certain height.
Okay, most likely it won't bounce back to the same height. Okay, in a real life situation. Even if you ignore air resistance, it won't bounce back to the same height. Because in a real life situation, 100% restoration of shape does not occur. Okay, even as I said, even diamond undergoes some deformation and perfect restoration may not, maybe 99.999 can occur, but 100% does not occur in a real life situation. Okay, let's say the coefficient of restitution between the ball and the ground is E. We don't know its value. Let's keep it as E itself. Okay. The ball is dropped from a height h. You need to find out to what height it rebounds. Okay. After the first collision with the ground. There's no air resistance. Derive the height to which it bounces after the first collision. It is dropped from rest. Initial velocity here is 0. Vanilla, can you tell what steps you are going to take?
Sir, can you repeat the question?
After striking the ground, to what maximum height does it rebound? Rishi, how will you find out?
Third, we'll use the MGH formula.
Which MGH formula?
But there's no 1 second. Think about it.
Vanilla,
So
if you can.
conservation of linear momentum.
Conservation of linear momentum between what and what? Or for which system are you going to write that equation?
So between the ball and the ground.
We don't know the mass of the ground, no? Mass of Earth. And we are observing with respect to ground. So before collision, ground will be at rest. After collision also, ground will be at rest itself. Okay, listen. You are asked to calculate the height to which the ball is going to rise. Can one of you tell me on what factors does the height to which an object rises depend? The maximum
Sure,
height.
the force applied to it while it's thrown.
Okay, but can you tell any formula for it, for the H max? It's true that
Velocity by which it goes up.
it depends on the speed with which it begins to rise. Okay, Vanilla, what's the formula for H max when an object is projected vertically upward?
Velocity u square by 2g, sir.
Okay, that is correct. Rishi, you said it depends on the force that is applied to project it in the upward direction. That's correct only, but when you apply force, the ball or whatever object it is that you are projecting gains some velocity before leaving your hand. Okay, it's that velocity which determines how high it's going to rise, and this is the formula for H max for a vertically projected body. H is equal to u square by 2g. Basically, the u here, okay, I better write it as v square by 2g, where v is the speed with which it begins to rise. Okay, so this ball, just before collision, it will have some velocity. Just before collision, we know it will be moving in the downward direction. And just after collision, it will move in the upward direction. So just before collision, I'll represent it in green. Let's say it has some velocity v1 like this. And just after collision, I'll represent it in red. Assume it has some speed v2 like this. Okay. How high it is going to rise after collision depends on this speed, the speed with which it begins to rise. So effectively, what you need to do first is find out the speed of the ball after collision. And to find speed of the ball after collision, you need to know the speed of the ball before collision, so that you can make use of this coefficient of restitution and determine with what velocity they separate. Okay, because coefficient of restitution is a ratio of speed of separation to speed of approach. Okay, to find out the height, what we need is the speed of separation. Now ground is at rest. It continues to be at rest after collision also. Okay, the speed of the ball itself becomes the speed of separation. And before collision, the speed of the ball, the speed with which the ball hits the ground itself becomes the speed of approach. So in this case, V2 is the speed of separation, relative speed of separation, and V1 is the relative speed of approach. Now, height depends on speed of separation, and speed of separation depends on speed of approach through coefficient of restitution, and speed of approach depends on the height from which the ball is falling. Okay, so there are three things that you need to find out here. You should first find out with what speed it hits the ground. Then you find out with what speed it rises from the ground. Then you find out the height to which it rises. Okay, try this, both of you. Get V1, then in terms of coefficient of restitution, get V2. With that, get the height to which it rises. Okay. Vanilla, what is your idea to calculate V1? The velocity with which it hits the ground.
E equal to v2 minus v1 by u1 minus u2, sir.
No, that is coefficient of restitution. Okay. But see, the speed with which it hits the ground is what I asked. This depends on the height from which it is falling, no?
Yes, sir.
So how will you get the expression for V1?
Square minus u square equal to 2gh.
You can use equations of kinematics. You can use mechanical energy conservation also. As the ball falls down, it loses potential energy, gains kinetic energy. The potential energy lost by it is mgh. Kinetic energy gained by it is half m v1 square. Okay, v1 is the speed with which it hits the ground. So you get v1 as under root 2gh. That's all. And we know this from before also, maybe you forgot. When an object falls from rest by a height h, it gains a speed under root 2gh. Rishi, is this clear?
Yes, sir.
Okay, that's the speed with which it hits the ground. Now, Rishi, you tell me, how will you find out the speed with which it bounces off the ground?
Sir, it'll be V2 is equal to V minus V1.
What is V? And where are you getting these equations from? Like in the previous problem also, you started saying 10 minus V1. Like where did you learn subtracting these speeds? And here also you are saying V minus V1. What is V? Okay, listen, both of you. Just look at this as a collision between the ball and the earth. Okay. V1, I have written here also. V1 is the speed of approach between the ball and the earth. And V2 is the speed of separation between them. That's all. And you have found speed of approach under root 2gh. If you know speed of approach, how do you calculate speed of separation? Vanilla, you tell.
Equal to v2 minus v1 by u1 by.
E, the coefficient of restitution, is the relative speed of separation by relative speed of approach. Here, since the second object, the earth, is at rest, the first object speeds itself will be the speed of approach and speed of separation. So speed of separation, you can call it V2. Okay, V2 is the speed with which the ball bounces back. The speed with which it bounces back itself is the speed of separation, no, from the earth. And V1 is the speed with which it hits the earth. That's the speed of approach. That's all. So you can say V2, the speed with which it bounces, is equal to E times of V1. That becomes E under root 2gh. That's the speed with which it starts rising from the ground after collision. Okay. And we know the speed with which it starts rising from the ground, then we can tell the height to which it rises. H is equal to V square by 2g. Therefore, the height to which it rises becomes, you have to square this speed V2. Okay, I'll write the formula also. V2 square divided by 2g. If you square V2, it becomes E square into 2g small h divided by 2g. 2g is cancelled. You'll be left with E square small h. Therefore, the new height to which it rises is E square times the original height from which it is dropped. Okay. The speed with which it rebounds is E times the speed with which it hits the ground. And the height to which it rebounds is E square times the height from which it is dropped down to the ground. Is this clear? Rishi, did you understand?
Yes, sir.
Okay. Now, if E is equal to 1, E equal to 1 indicates an elastic collision. 100% restoration. If there is 100% restoration of shape, then the height to which it rebounds will be equal to the height from which it is dropped. So it will rise to the same height. Suppose E is less than 1. You square a number less than 1. Its square also will be less than 1 itself. For example, 0.5 square is 0.25. So if E is less than 1, okay, I'll mention it here. E square is also less than 1. That means capital H will be less than small h. The height to which it bounces will be less than the original height from which it is dropped. Okay, it won't rise to that much height. That is what we observe in daily life situations. Okay, and if E is 0, it won't bounce at all. It will like hit the ground and stay there. That is what happens if you drop a lump of wet clay onto the ground. Okay, wet clay or dough. Okay? You drop it onto the ground, it just like kind of sticks to the ground without bouncing back. So there, it's a perfectly inelastic collision. E becomes 0. Okay. So the first time this ball bounces off the ground, it rises to a height E square h. Okay, we can visualize it like this. So let this be the height E square h. So after the first bounce, it goes to that level. Then when it reaches this level, it starts coming down and it will bounce for the second time from the ground. Tell me, after the second bounce, to what height will it rise? After first bounce, it goes to a height of E square h. Then it starts falling down again due to gravity. Then the second time, to what maximum height can it rise? You don't have to solve anything, you can answer directly.
E cube, let's say.
E cube. Why do you say E cube?
Sir, E power 4h.
It will be E power 4. Okay. See, the logic is when it's dropped from a height h, it's bouncing to E square h. Second time when it falls, it's falling from a height E square h. If it falls from this height, then it rebounds to E square times of that height. So it becomes E power 4h. Okay, so that's the height to which it rises the second time it bounces from the ground. Rishi, did you understand the logic?
Yes, sir.
Rishi, you tell me, when it bounces off the ground for the third time, to what maximum height will it rise?
Sir, is it e to the power 8?
Think carefully and answer. No, it's not e power 8. It's falling from a height of e power 4h. Okay, when it bounces for the third time. To
Oh,
what
it's e to the power 6.
it will be e square into e power 4h becomes e power 6h. Next will be e power 8h and so on. Okay, it will keep bouncing. Fine. Now in this same situation, like, see, if E is non-zero, E square h, E power 4h, E power 6h, they'll all be non-zero values only. But the height will keep on decreasing. At one point, we won't even be able to notice the bounce in a real life situation. Okay. So you know what distance it is falling, what distance it is rising. Again, what distance it is falling, what distance it is rising. We can write an expression for that in terms of E and the original height from where it is dropped. So now the question is, derive an expression for the total distance moved by the ball before coming to rest. Try this. Any answer for this? Little bit of mathematics is involved in this. Okay, Rishi, tell me, from the instant the ball is dropped, okay, till it hits the ground for the first time, how much distance is it traveling?
H, sir.
H in the downward direction. Okay. Then it bounces off. It rises to a certain height, you know how much, and then it comes back. Tell me, from the first collision to the second collision, or between the first collision and the second collision, what distance is the ball traveling?
E square H.
That's all. Vanilla, what do you say? Between the first and second collisions, how much distance is the ball traveling?
2e square H, sir.
2e square h. It rises e square h, again falls also. Okay. So 2e square h. Rishi, you tell me now. Between the second collision and the third, how much distance does it travel?
2e to the power 4h.
2 times e to the power 4 h. And between third and fourth collisions, it will travel 2 times e power 6 h and so on. You will have infinite terms like this. You have to calculate the sum of these infinite terms. Okay, so here you will have to use your knowledge of progressions. Okay, sequences and series you must have learned. Can any of you identify or point out a series in this, a progression in this?
So e square e power 4.
E square, e power 4 and so on. But there's a 2 term also. The first term doesn't have 2. So what you can do is put the first term h aside. You look at the remaining terms in this sum. Okay. Basically, this is a geometric progression, GP. Okay. And it's a geometric progression whose first term is 2e square h. Like in terms of, like in the terminology that we use in sequences and series, we represent the first term as A. Okay. So first term is 2e square h. And from then onwards, you can see that they are getting multiplied with e square. So you can say it's a geometric progression with first term A and common ratio e square. Okay. From term to term, whatever is getting multiplied is what you call as common ratio. Okay. Fine. So basically, the total distance traveled by the ball becomes the first height by which it drops, and then the sum to infinite terms of this GP. Can any of you tell me a formula for sum to infinite terms of GP? In terms of A and R, first term and the common ratio.
Sir, A by 1 minus R.
A by 1 minus R. Pawan, can you tell me when that is valid? Sum to infinite terms of GP is not always given by this formula, but there's a condition for this. Okay, this is valid only when R is less than 1. If common ratio is more than 1, you can't use this. Okay. Now here in this progression, R is e square. We know e is a number between 0 and 1. Okay. So if E is between 0 and 1, E square will also be between 0 and 1. So you can say that the common ratio here is less than 1. So this can be used. Fine. Therefore, the total distance traveled by the ball before coming to rest finally on the ground will become h plus a. The initial term of this GP is 2e square h divided by 1 minus the common ratio of this GP is e square. So that's the total distance traveled. You can take LCM and simplify this. It becomes h into 1 minus e square plus 2e square h whole divided by 1 minus e square. Changes to h minus e square h plus 2e square h becomes plus e square h divided by 1 minus e square. You can express this as h into 1 plus e square by 1 minus e square. That's the total distance it travels in all the infinite bounces that it does. Okay, so let's go through this once again. A ball is dropped from a height h above the ground. We first found out to what height it rebounds after the first collision. The height to which the ball rebounds depends on the speed with which it bounces off. And the speed with which it bounces is basically its speed after collision, which depends on the speed before collision. You can relate them through coefficient of restitution. And speed before collision depends on the height by which it is falling. So speed before collision v1 is under root 2gh. Then after collision, it bounces with a speed e root 2gh. And if you know the speed with which it bounces, you can tell the height to which it bounces. And it happens to be e square times the height from which it dropped. Okay. So if it falls from a height h, it rises to e square h. Second time it will fall from e square h, so it will rise to e power 4h. Third time it will fall from e power 4h, it rises to e power 6h, and so on. You get that GP. Add that, you'll get the total distance traveled before finally stopping on the ground. That stopping happens after infinite number of bounces, but still you can find out the total distance because there is a way to find out sum to infinite terms. Okay. Basically, another idea we used here is like how this question was different from the earlier questions that we solved on collisions is that Earth is the second object here in this collision. One object is the ball, the other object is the Earth. We have taken Earth itself as a reference. Okay, so before collision, Earth is at rest. After collision, also Earth is at rest. So the ball's speed itself becomes the speed of approach, and after collision, the ball speed itself becomes the speed of separation. Okay, normally, when two objects like this collide, speed of separation is calculated as v2 minus v1. Okay, but here, since one of the objects was the reference, the other object's speed itself is the speed of approach, speed of separation. Okay, I'll give you some more questions like this for practice in the worksheet you can solve. Next, let us discuss what to do if it's a two-dimensional collision or an oblique collision. Basically, in a 1D collision, what happens? 1D collision is also called as a head-on collision. What happens is the object, the colliding object, moves along the line of impact. You know, this is called the line of impact. Okay, the line along which the normal force acts. So all the action happens along the line of impact itself. Such collisions are called 1D collisions or head-on collisions. Okay, but consider a situation like this now. Let's use this same ball. Ignore gravity for this problem. Okay, let's say there is a wall here or a surface here. It's a fixed surface. Or maybe we can use carom coins. Just a moment. Carom board placed on a horizontal surface. Frictionless carom board we'll consider. 1 second. Let's say this is the border or the edge of a carom board. Consider the striker like this. Okay. That frame will be there, no, the black frame. That is what you are seeing. I have not drawn the board and all. Assume the striker is moving towards towards the border along this line. Okay. So its velocity is in this direction. Let's call it as u. Now, the moment it comes into contact with the frame, if you visualize, the striker will be here. Let me adjust this. Situation will be like this. The striker will be here. Okay, maybe slightly to the left. Somewhat like this. What will happen the moment the striker comes into contact with the frame?
So the other part will go bounce to the other side of the square.
Okay, but what does the frame do to the striker when it comes into contact with it? You have to talk in terms of forces.
Does it apply some sort of normal force? Because
Yes, it applies normal force. In a real life situation, there will be some friction also, but for now, let's assume the surfaces are all smooth. Okay, collisions with friction, you need to know, okay, it is important for JEE Advanced. For now, we will assume they are smooth surfaces. So when the moment the striker comes into contact with the frame, a normal force starts acting on it. Normal force acts this way. It acts at the point of contact. Now, if normal force is acting like this, then this line becomes the line of impact. It's very important to visualize the line of impact while solving problems based on collisions. Okay. And due to this normal force, its velocity is going to get disturbed. So what we'll need to do is find out its velocity after collision. And why I'm telling you that we will ignore friction, that also you understand. Before collision, just before collision, the striker has a velocity in this direction, right? Okay, it'll be better if you visualize this separately. Let me just consider the striker. Right. Imagine the striker just comes into contact with the surface. Now, when it comes into contact, you know it will undergo some deformation. It won't be this much. You won't even be able to notice the deformation. I'm exaggerating it. But there will be some deformation at the molecular level. Okay. So when this happens, or when the striker comes into contact with the surface, it had velocity in this direction, okay, at an angle. So basically, it has some velocity parallel to the surface, and it has some velocity perpendicular to the surface as well. Now, due to the velocity parallel to the surface, okay, this component, it will have a tendency to get dragged along the surface. Now see, the carom coin coming into contact with the surface, undergoing deformation, and then again relaxing. There are multiple stages here, right? You can visualize it like this. This is just at the instant of collision. I'll send this back. Okay, just when it collides, it is in perfect shape. During collision, deformation occurs, and it again gets back to its original shape more or less. Okay, by the time the collision is complete, okay, it will get back its original shape. Or if the coefficient of restitution is less than 1, it may not perfectly get back its original shape also. So these are the different stages of collision actually. Okay, coming into contact, collision starts. It goes up to maximum deformation and then restoration happens. In this process, what will happen, or during this deformation and restoration, this horizontal component of velocity that is there, okay, I think it's better I represent it in black itself. This horizontal component of velocity that is there, it will drag the carom coin along the surface of the, along the frame. Up to some distance, it will slide along the frame. Of course, it's a very short distance. While playing caroms, you won't even be able to notice how much it slides parallel to the frame before it rebounds. Okay, because collision happens in a very short interval dt. In that interval, the distance by which it slides along the frame distance will be that component, x component, multiplied with the time. Okay, it will be a very short distance. But as it is getting dragged along the frame, friction will act on it. If it's a rough frame, friction will act on it in the backward direction, and friction can disturb this component of velocity. Okay, we'll discuss this in detail later. For now, let's assume it's a smooth frame. Then the component of velocity along the frame will not get disturbed. Which component will get disturbed? The component perpendicular to the frame. That is, the component along the line of impact will get disturbed. So it's very important to resolve the initial velocity into two components. See, this is the actual direction of the initial velocity. I'm taking it as it is. We'll have to split it into components now. One component along the line of impact, I'll call this as V parallel. Parallel to what? Parallel to line of impact. Okay, or for now I can call it as Vy also, not V, U, initial velocity is U. So I'll call it as Uy. The other component perpendicular to line of impact is like this, Ux. Okay, so this is just before collision when normal force starts acting on the carom coin or the striker. We have resolved the velocity into components, that's all. We didn't do anything beyond that. Now we will see what the situation will be like after collision. Okay, assume it's a smooth surface. We are not considering friction yet. So just after collision, tell me which component of velocity would be disturbed, Ux or Uy?
UX, sir.
Why will Ux be disturbed? Which force disturbs that component of velocity?
Oh, it's UI.
Which force disturbs Uy?
Then U.
U is not a force, U is a velocity.
Then it's the normal form, yeah.
Okay, it's the normal force which disturbs the Y component. Okay, the component along the line of impact. So after collision, the component along the line of impact, let's say it changes to this. It will have some velocity in the Y direction, and the X component will stay as it is because there was no force acting along the frame. There's no friction, no? So the X component will not change. The Y component will have changed. Before collision, it was moving towards the frame. After collision, it moves away from the frame. So the Y component will go that way, will be that way. And the resultant velocity of the carom coin after collision, X component, Y component, as a result, it bounces off like this and travels this way till it hits the other edge of the carom board. We are assuming the carom board to be frictionless. Okay, so this is what happens. Now what we have to find out is, based on the nature of collision, whether it is elastic, partially inelastic or perfectly inelastic, we have to find out this Y component. Once you find out the Y component, you can get the total velocity of the coin after collision. And basically in collisions, that is what our aim is, to find out velocity after collision. Okay, and to find out this Y component, what we are going to do is, we are going to consider the components only along line of impact. We will treat it as a 1D collision along the line of impact. That's all. So along line of impact, this y component is the speed of approach. And along line of impact, this final y component is the speed of separation. And you know these two are related by the coefficient of restitution. So we can write E is equal to speed of separation is Vy divided by speed of approach is Uy. So from this you can get the y component of the final velocity. Once you do that, you know the final velocity completely. That's all. Okay. So in oblique collisions, now why am I calling this an oblique collision? Clearly you can see the motion of the objects is not along the line of impact. Okay, such collisions are called oblique collisions or 2D, 3D collisions, you can say. So this is the basic idea. Imagine the objects in contact. When they are undergoing a collision, imagine them to be in contact. Visualize the line of impact. Now here, we took the case of a striker hitting the edge of the carom board. Edge of the carom board is at rest. Striker is moving. So one object is moving, the other object is at rest in this case. So for the moving object, we wrote velocity components along line of impact and perpendicular to line of impact. And along the line of impact, we treat it as a 1D collision and find out the final velocities component. And then we know the total final velocity. But this is a simple case where the second object, the edge of the carom board, is at rest. Okay, the carom frame is at rest. It's also possible that the second object is moving, like two spheres colliding in air, or two moving carom coins colliding. That's also possible. If both objects are colliding, resolve both their velocities along line of impact and perpendicular to line of impact and solve the problem. Okay, so oblique collisions are going to be, finding velocities in oblique collisions is going to be a slightly lengthy process. But if you resolve or if you take the components correctly, then it becomes simple. Okay, so let's solve this problem. Consider this case itself. Carom striker hitting the edge of the carom board. I'm not drawing the entire board and all. Assume the striker is moving towards the frame of the carom board along this line. Okay, that's the initial line of motion. I'm not showing you the line of impact. You have to visualize the line of impact. So it's moving along this line. And let's say it's moving with some 20 meter per second speed. It's a smooth surface. The edge of the carom board is smooth. Coefficient of restitution between the striker and the edge, let's say is, okay, take 0.5. Calculate velocity of the striker after collision. Needless to say, the frame is at rest before and after collision, okay? Only the striker is moving. Okay, I have to give you at what angle it was moving. 53 degrees. I hope you all remember these values. Sine 53 degrees is 4/5. Cos 53 degrees, 3/5.
Sir, can you scroll up a bit once?
Okay, wait 1 second. Don't blindly use the formula and solve. Resolve into components. visualize what is speed of approach, what is speed of separation, use the equation for coefficient of restitution and all.
Yeah, so you can say.
Okay. I got one answer as 12 I cap plus 8 J cap. Okay, I think that is correct only. Rishi, can you tell how you are trying to solve this? You need to find out the velocity of the striker after collision. So what should be done?
Sir, so when it collides, it's going to ux will be sir, wait, I'm not sure about this.
Okay, you have to get the components and then. Okay, Pawan,
With
can
the
you
components,
tell? Continue.
and then Vy will be something like
Okay, fine. See, we resolve the initial velocity into components along the line of impact and perpendicular to line of impact. So the first thing to do is to visualize the line of impact. Now, when the striker comes and hits the edge of the carom board like this, we know that the line of impact is going to be the y-axis. Okay, I'm not fine. So this vertical line is the line of impact. That's the line along which the normal force is going to act. I should not say vertical, I should say line in the y direction. Okay, so that's what I did. The initial velocity 20 will resolve it into components. Pawan, can you tell the x component and y component?
Sir, x component is 12 and y component is 16.
12 and 16. Okay, 20 sine cos 53, 20 sine 53. Okay. Pawan, tell me which component will get disturbed by the collision? 16 component or 12?
Sir, 16.
16 will get disturbed. Okay. And in fact, we know it is going to like reverse in direction. Like after collision, this 12 component stays as it is. Okay. So I'm showing it in red. It stays as it is. And you will see the striker getting a velocity in this direction after collision. Let's call this as Vy. Vx is same as ux, that is 12. So after collision, we know the x component. What we need is the y component. Okay. And the frame of the carom board is at rest before collision, and after collision also it's at rest. Therefore, the speed with which the striker hits the frame along the line of impact, this itself is the speed of approach. Okay. And the speed with which the striker goes away from the frame along the line of impact, not the final speed. Only the speed velocity component along line of impact is what matters for approach and separation. Okay. This is the speed of separation. Okay. And we know speed of approach, speed of separation are related by coefficient of restitution, this one. So we will make use of it. We will write E is equal to 0.5 is equal to speed of separation divided by speed of approach, initial velocity in y direction I will write. Therefore, 0.5 becomes Vy divided by, how much is the speed of approach? 16. Therefore, speed of separation along the line of impact becomes 16 into 0.5, that is 8. That's all. So this component is 8. The x component is 12, y component is 8. Therefore, the final velocity of the striker, that is its velocity after collision, will be 12 I cap plus 8 J cap meters per second. You can tell at what angle it rebounds also. Once you know the velocity, just draw the vector. 12 I cap will be this way, 8 J cap will be this way. The striker is going to rebound at an angle like this. You can tell what angle it makes with the frame. This is 8, this is 12. So it's like 2 and 3. Tan theta is equal to 8 by 12, 2 by 3. Or theta is tan inverse 2 by 3. That's the angle at which it bounces off from the frame. Okay, you can tell impulse, change in momentum, all those things also. Okay, just think about it once again, ask if you have any doubts. Is it clear to all of you?
Yes, sir.
Yes, sir.
Okay. Now try another question. Just a moment. Okay, let's use this itself. Suppose there are two strikers now. Okay. Let's say one is here and another one is here. We can call them as A and B. They are of equal mass and collision is going to be elastic. Okay. Last class, we derived one result. In a 1D collision, when two objects of equal mass undergo elastic collision, what happens? When two objects of equal mass undergo elastic collision, what happens?
V1 equal to U2, sir.
So we can say that their velocities get exchanged. Okay, when two objects of equal mass undergo an elastic collision, their velocities will get exchanged along the line of impact. Means first object's velocity along line of impact will go to the second object. Second object's velocity along line of impact will come to the first object. Okay, so let's assume this is one striker in black. One second. The other one will take it in blue. Okay. Now, the first striker is moving in such a way that, okay, second one is at rest. B is at rest. A is moving and it is moving along this line. Somewhat like this. Such that when it just comes into contact with the second striker like this. Fine, that's the line along which the first one is moving. So when it comes into contact like this, you know they will exert a normal force on each other. I'm helping you in all that visualization. Normal force will act along the line of impact. This is perpendicular to line of impact, the x-axis. Once again, in this problem also, the y-axis is the line of impact. Okay. Let's consider the same situation as before. This striker is moving with 20 meters per second. At an angle 53 degrees with this line. Okay. Find out velocities of both the strikers after collision. Right? You are told that it's an elastic collision and that their masses are equal. Now see, let me explain another difference between this problem and the previous one. In the previous one, the frame was at rest. So you knew with what velocity the striker was approaching. You had to find out with what velocity it separates. So one equation was sufficient, coefficient of restitution. But here, when one coin goes and hits another coin, the second coin also can move. So you'll have to find final velocities of the first coin as well as the second coin. This time you're going to need two equations. You will have to apply momentum conservation also. Okay, try. Any answer, anyone?
The velocity of object is 12 I cap and velocity of P is minus 16 J cap.
Okay, 12 I cap minus 16 J cap. We'll see. Now see, just before collision, when A is at this position, you can resolve its velocity into two components. The component along the line of impact will be 16. The component perpendicular to line of impact will be 12. This we have done in the previous problem also. Based on the angle, initial velocity and angle, you can get this. Rishi, tell me, which of these components will be disturbed by the collision?
16, sir. 16.
16 will be disturbed because that is along the line of impact. We assume the strikers are smooth, so no friction. 12 will not be disturbed, 16 will be disturbed. So after collision also, the first striker, that is A, will continue having this 12 I cap component. This will stay with it. Okay. And let's see what happens to the 16 component. Observe this carefully, all of you. I told you, you just have to treat it as a 1D collision along the line of impact. Once you get the velocity components, treat it as a 1D collision along line of impact. Because other component you already know. Okay. This red dotted line is the line of impact. Now what is happening? This is an elastic collision and you know the masses are equal. In an elastic collision, if masses are equal, their velocities will get exchanged. Means that 16 component that is there goes to the other striker, that's all. The second striker was at rest. That velocity will come to this. So this thing's y component becomes 0. Okay, the first striker's y component becomes 0. Second striker gets that y component 16. You don't have to apply momentum conservation, coefficient of restitution, because this is a case we have already solved. Okay, equal masses, elastic collision, velocities get exchanged, we know that. So the 16 of the first striker goes to the second striker. The 0 of the second striker goes to the first striker. Exchange of velocities along line of impact. Okay, along line of impact, this is what happens. Now visualize the complete picture. What is the complete picture? The first striker already has this component 12. That component stays with it. Y component is 0, but X component is 12. Therefore, the final velocity of the first striker is 12 meters per second I cap. And the second striker, it didn't have any velocity, it got this 16. Therefore, the final velocity of the second striker is minus 16 J cap. Okay. So effectively after collision, what will happen? Just a moment. I'll remove these velocity components just to help you visualize. Just before collision, A was moving at an angle like this and B was at rest. Okay, A was moving this way. After collision, A only has its X component. So what happens is A hits that striker B and goes off like this. A travels along this line. Possible you all must have observed in caroms, it can happen like this. So it's moving like this initially, hits that other coin and then goes this way. And what about the second one? The second one gets the y component of velocity. It starts traveling in this direction. This is what the final situation will be like. Okay, is the solution clear to all of you? Any doubt in this? Rishi, did you understand?
Yes, sir.
Pawan, what about you?
Yes, sir.
Okay, fine. So this is how to deal with 2D collisions. Resolve their velocities into components along line of impact and perpendicular to line of impact. And along the line of impact, which you must visualize, treat the collision as a 1D collision, get the final velocity components. And then you know the overall final velocity of the colliding objects. You can tell how they will move after collision. Okay, we'll solve some more problems based on 2D collisions in the next class also. And we'll briefly discuss about power. Okay, how to calculate power. Okay, definition of power, how to calculate it, and how to make use of power to find out some other things about an object. Okay, so today is what? Wednesday. I will be taking one class tomorrow. It'll be a short class, maybe 45 minutes to 1 hour. And then Friday, you'll have your regular class. Tomorrow, Friday, we'll finish this chapter. So that next week we can start system of particles and rotational motion. Okay, thank you all. We'll continue tomorrow. Timings I will inform. It will most likely be from 8:30 to 9:30. Okay. Yeah, we'll fix it 8:30 to 9:30 tomorrow.